All right, so now we move on to lesson 1.5, which deals with infinite geometric series. So as we know, geometric means that we're either multiplying or dividing to get to the next term. And when we talk about series, it means we're adding a select amount of terms together. When we tie this word of infinite into that, when we say an infinite series, we're saying that there is an infinite amount of terms or an unlimited amount of terms. So there's no sort of finiteness to it. Now, this can be broken apart into two different types of infinite series, one which actually allows us to calculate some sort of sum, and the other one which we can't do anything with necessarily. As soon as we identify that it is this form, we cannot use it. So the first form is convergent, and to converge means you're approaching some value, but you don't actually end up reaching it. And that's an important thing to highlight there, is when we converge, we approach, but we don't actually reach there. We get to some specific number, whether that be something in the hundreds, something really small, something really large, but we never actually get to that number. We just approach it in that way. Now, when we test for this convergence or test to see if we approach a specific number, we want to be looking for a given fraction or a common ratio, as we called it in this unit, where it's between 1 and -1, and strictly between -1 and 1. If it's a 1 or -1 or greater than those two, then we're going to call it something else. But for this one, we want to have a value that's strictly between 1 and -1. And then that will allow us to use the following formula from our formula sheet, where we can say if our common ratio is somewhere between +1 and -1, not including those end bounds, then we can use this direct formula from our formula sheet that says, hey, if we want to calculate that infinite sum for some first term which is divided by 1 minus the common ratio, we'll approach some sort of specific value in terms of a sum value. Now, in the other case, which is the non-calculable type, we look at divergent sequences or divergent series. And these are infinite series which diverge away from a value or diverge to some sort of general infinity. And when we look at this, these do not include sums that can be calculated in this situation. So we wouldn't want to go to our formula sheet. And more importantly, this is for all values, again, that are included where it's greater than 1 and very particular, strictly greater than 1, or where the common ratio is strictly less than -1, which means we could have values like -2, -3, -4, or 2, 3, 4, and onwards and onwards. And obviously, fractional amounts between there, but we look at them and we say these series will diverge away from values and they'll actually go to either positive infinity or negative infinity. And because they're diverging in this way and they're not approaching a specific value, there's not actually a way to specifically calculate the overall sum or a specific sum in which they're approaching. So when we look at this piece here, we're going to do a quick test for both these cases, and we want to determine right away if they give you some sort of series in this situation, again, because we're in the geometric series or infinite geometric section, we're going to highlight both of those together, so I should make sure I have that. We can figure out if it's convergent or divergent just by doing a simple test here. When we look at them, we want to be thinking, what is that common ratio that separates them? And that will simply tell us all that we need. So for the first one, if I look at the sum of the first term, well, the first term in this given series is 16. Then the next two added together make 24, 16 plus 8. 24 plus 4 gives us 28. 28 plus 2 gives us 30, on and on and on. And to figure out the overall sum, when we look at this, we're like, okay, well, can we actually calculate a value? We can, and here's the reason. When you go between the values from 16 to 8, so if we take the common ratio, we take 8 and divide it by 16. This is equal to 1/2. And 1/2 is clearly strictly less than 1. Therefore, we can say that because the R value is less than 1, this is actually a convergent sequence or convergent series. And if it is convergent, we can automatically use the formula where we said that S infinity, or the sum of the infinite terms, is equal to the first term divided by 1 minus the common ratio. Now, let's put that into action here. S infinity is equal to T1 was 16 for us. So we're going to go 16 divided by 1 minus 1/2, which is the common ratio. And this is going to end up giving us that 16 divided by 1 minus 1/2, that's 16 divided by 1/2, which is the same as 32. So the sum in which we approach this overall geometric series sum is 32. That's the value we're approaching as we add up this infinite geometric series here. Okay, now again, the reason we could do this is because the value for the common ratio was strictly less than 1 or strictly greater than -1, or less than -1, I should say. And if that's the case, we're like, as long as it's between 1 and -1, we see it's convergent, we can apply this formula. Now, we go to part 2, or part B, I should say. For this one, we're going to do our common ratio test. So common ratio is equal to 1 divided by 1 over 2. This is the same as 1 times 2, which gives us a common ratio of 2. If I do this test again, I can go 2 divided by 1, or the third term divided by the second term. This is going to be equal to 2, and therefore, if I get a value of 2, we can say that because the common ratio, which is equal to 2, is greater than 1, this means that this is a divergent series. And as soon as we know it's divergent, there's no way to calculate the sum. So if we want to just put that below, we're going to say there is no sum for this series here, because we're thinking about it in terms of it diverges, it doesn't actually approach a value, so we cannot calculate a given sum for this. All right, now let's go to our next page here. Determine whether each of the infinite series converge or diverge. If it converges, calculate the sum. So very similar to what we did on the previous page, just a little bit more applied and a little less guided on our aspect. So first and foremost, we want to figure out what the ratio is, right? So we're going to go common ratio is equal to any two consecutive terms divided. So I'm going to take term 2 divided by term 1. This ends up giving us negative 1/3. And because negative 1/3 is contained between the negative 1, or it's greater than negative 1, but still less than positive 1, we can therefore say that this is convergent. So I'm just going to put that below here. Therefore, this is convergent because it follows the property of this convergent nature. Now we can actually calculate it using the formula of S infinity equals T1. The first term for us was 27 divided by 1 minus a negative 1/3. When you plug this into your calculator, this is the same as 27 divided by 2/3, which ends up giving us 20.25. And then I'm also just going to give it in the fraction form. In your calculators, that conversion is quite simplistic. So we're just going to put both of them there, just in case they ask for a fraction or the decimal, either one. Okay, we're going to do that exact same thing over here. We're going to first of all see what our common ratio is. So ratio is equal to, I'm going to take second term divided by the first term, which is equal to -2. And then just to test out that it is actually -2, you could do it one more time. Let's say I take the fourth term and I divide it by the third term. This is also going to give me -2. Now, as soon as you see that this is -2, you're like, wait a minute, if the ratio, which is equal to -2, is less than -1, that means that we're in a bad situation where this is a divergent series or that there's no sum. So I'm going to write out that full thing. Divergent series, and then in brackets, I'll be like, there is no sum for this. Because how can we calculate a sum of something that diverges or that would continuously go on and on and on and get larger, 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 or get smaller, smaller, smaller in that sense? And there's no definite end. There's nothing that it approaches in that way. Because again, the language around this is when we talk about convergency, it's when it approaches a value, not actually hits a value, whereas divergent, it never approaches any values. So there's no way to calculate that infinite sum. All right, now let's go to example 3, where they give us the following situation, which is a pretty applied example. I like it. In the first month, an oil well in Manitoba can produce 36,000 barrels of crude oil. And then every month after that, they produce 95% of the previous month's production. So essentially saying they lose 5% of the overall production month to month. Now, they want us to list out this terms in this given series that represent the number of barrels produced. So first and foremost, in the first month, they said they produced 36,000. Easy peasy. Plus, we're going to add up the next month's barrels. To do that, here's what we do. The value we're going to get is 34,200. How did I get that? I take this first value, which is 36,000, and you multiply it by 0.95. When you multiply any number by the decimal format of its overall percentage, you're going to figure out that this will give you the next value. So we're going to multiply it by 0.95, aka 95% of the value, and we end up getting that we add 34,200 barrels the next month. We're going to repeat that process a couple more times. The next month, I would produce 32,490. And then the next month after that, I would produce 30,865.5. And then I'm just going to put 3 dots indicating that this is an infinite geometric sequence that eventually will approach 0. But we don't know how many months that would take. We're just going to repeat that process a couple times here and just say, hey, we multiply, and then we get to here, and we don't know where it ends. Now, they say, if this trend continues, what will be the lifetime production of the well, aka when will the oil run out in such that we've produced all we possibly can? Now, to do this, here's a couple things we want to make sure we write down here. First and foremost, we know that the common ratio, and I'm going to make sure this is in black, the common ratio, r, is equal to 0.95. This is how much we're either adding or shrinking by, I should say expanding or shrinking, because we're talking about it as a multiple. We're shrinking in this case by 5% every month. And then the first term, which is T1, is equal to 36,000. That's the initial production we get out of this well in Manitoba. Now, because we're going to assume that if they say that we can calculate something based on this trend, we're going to assume that this is a convergent series. And when it converges, we can use the formula of S infinity, or in its lifetime, in the lifetime we're considering, it will be equal to T1 divided by 1 minus R. T1 is 36,000 barrels, divided by 1 minus the ratio value, so 1 minus the 0.95. And then this will give us 36,000 divided by 0.05, which gives us a lifetime production or overall sum of this given series of months of production of 720,000 barrels. So we're going to write barrels may be produced. Perfect. Now, again, the tough part about when we do these calculations is realistically, we're just approaching this value. So this would be the absolute maximum that we would be ending up approaching. We may not exactly hit this because when we talk about calculating these series and it's a shrinking of 95%, there's actually an infinite amount of terms that can exist between term one and the term that would give us this overall sum. So realistically, we're just saying that it approaches this value, and that if this was in reality, there would always be that next little bit we could produce that would be a fractional amount of that original quantity. I know that sounds really complicated, but just think about this as a value we're approaching, saying we're approaching that when they do their lifetime production, they'll approach 720,000 barrels possible. All right, let's go to example 4. The sum of an infinite geometric series, again, just like we did in our previous lesson of 1.2 and 1.4, if they tell you the specific series or sequence it is, I would just recommend highlighting that. And they say, if we know that the sum of the infinite geometric series is 92 and the common ratio, or the R value, is 0.25, what is the fourth term in this series? Now, to do this, here's what I'm thinking. First of all, we got to figure out what term 1 is, because we know what the sum is, we know what the ratio is, we just don't know what T1 is, and that's a very important information. So I'm going to go step number 1. We're going to write S infinity, because we're dealing with an infinite geometric series. There's only one formula for this, is T1 divided by 1 minus R. I'm going to plug in what I know. My infinite series, when I sum it, is equal to 92. So 92 will be on this side, is equal to the term 1, which we don't know, divided by 1 minus 0.25. Continuing our work here, which I'll put a little arrow up here, 92 is equal to T1 divided by 0.75, and we take 1 and subtract 0.25. And then when I multiply the 0.75 up, because I want to get it out of the denominator, so 0.75 times 0.75, what this is going to do is give me that my first term, or the first term in this infinite geometric series, is going to be equal to 69. Okay, now once we have that first value for our term 1, step 2 is actually quite easy, because to figure out any sort of specific term in this, or more importantly, the fourth term, we write it as fourth term is equal to, because this is a geometric series, we're going to use the geometric formula T1 times R to the n minus 1. Our n is 4, so I'm just going to throw that in here. That means that T4 is equal to T1, which is 69, times the common ratio, which is 0.25, all raised to the power of 4 minus 1, which is 3. And you plug this into your calculator and you figure out that the fourth term in the infinite geometric series is going to be 1.078, or as a fraction, 69 over 64. Now, for some of you that are like, wait a minute, that value is so low. Why is that value lower than you might expect? Because when we add these terms together, we get 92, but the fourth term in that series is going to be 1.078. Think about it as the following. This just means we have a huge amount of terms to add together, because if by the time we get to the fourth term, it's a really low number and our first term is 69, we're like, okay, it goes from 69 to T4, which is 1.078, we're going to have to add up a ton of terms in order to build it up to this 92, maybe even in the hundreds of terms, which that could be another part of the problem, is asking you to solve for that. We don't, so we're just going to leave it at this. Now, example number 5. We have an infinite series. We have 5 plus 5x plus 5x squared plus 5x cubed. You can clearly see that the pattern is that we're multiplying by another x every time we go up. and it says it has a sum of 4. So when we add up this infinite series, we can write S infinity is equal to 4 in the end. Now, the other piece of information is that we know the first term in this given series is 5, and then the R value is equal to X. Every time we go to the next term, we're multiplying it by another X, because to go from X to X squared to X cubed, you're just adding another X, and by power rule, or by product rule, I should say, X times X will add another X. Okay, now we're going to figure out what this specific X is that makes this true. To do this, what we're going to do is write S infinity, which is equal to 4, is equal to the t1, which is 5, divided by 1 minus x, which is the common ratio, or 1 minus r, from our formula sheet. Now, they asked us to state the restriction. We're going to do that very quickly here, and I'm just going to do that in red. The restriction is we can't have a denominator with x being 0. Or more importantly, we can't have a denominator that's 0. So really quickly, I'm just going to interject and be like, well, 1 minus x cannot be equal to 0, because if it is, then it ruins the fraction and makes it actually not a real number. And then we want to look at this and say, well, that means that if I add the x over to the other side, x cannot be equal to positive 1. So there's our restriction step. We've taken care of that. Perfect. Now we actually want to solve for this value. To do this, I'm just going to arrow over and continue this step. We're going to multiply everything that was in the denominator to both sides, so to the right, to the left. When we do that, it's going to give us 4. 1 minus x is equal to 5. We expand the 4 in. 4 minus 4x is equal to 5. I subtract both sides by the 4, so minus 4 and minus 4. 5 minus 4 gives us negative 4x, which is equal to 1. Lastly, I'm just going to divide by the negative 4. And I end up getting, whoops, I should have a negative here. We get that, therefore, x is equal to negative 1/4, where x cannot be equal to positive 1. Now, in this situation, it's not going to be equal to positive 1 because we got a specific value of negative 1/4. But just in case, let's say the x turned out to be 1, then by our restriction, it would be impossible and there'd be no solutions such that this series would add to a sum of 4. But for this situation, we do have an x value that would allow us to get a sum of 4 if we plugged it in. Awesome. Okay, let's go to our next page here. So this one's a bit applied, and it's going to be the trickiest one of the whole section, I would almost say, just in the way you have to approach it. So they say express this repeating fraction of 1.24 in a form using the concept of an infinite geometric series. Now, here's the way we have to approach this that makes this problem quite difficult. We have to break this number into a sequence or a series of the terms being broken apart. So here's what I mean by that. I'm going to take the 1, which is that leading 1 in front of the decimal, and I'm going to write it out front. And then what I'm going to do is just break this decimal, this repeating decimal, down into an infinite series of terms. So what I'm going to do is go 0.24, which was the first part of the decimal, plus 0.00. I skip over those points and write the next repetition, which is 0024. Then I'm going to write the next repetition, which is 000024. So I'm adding another 2 zeros, and that pattern would continue infinitely. Put a bracket. Now, there's a couple things we're going to pull out of this. If this pattern repeats, this 2, 4, 2, 4, 2, 4, and I've broken it apart into these different parts of 2, 4, we know the following. Ignoring that the 1 is out front, the t1 is equal to 0.24. That's the first set of repeating decimals that are in this. The other thing we can pull out of this is that the r value is equal to, we can take any two consecutive terms of these decimals and divide them, let's say 0024, divided by 0.24. So these are consecutive terms in that given series. When we divide them, we end up getting that the common ratio, or from one to the next, is we divide it by 100, which should make sense. We're just getting more and more small in terms of the decimal. We're adding 2 zeros every time we go to a new position. So it went from 0 zeros to 2 zeros to 4 zeros. We're basically adding 2 zeros, which is another way of saying divide by 100. Now, here's how this helps us in this problem. For step number 2, once we've broken apart this number into this series of given decimals, we can say that the infinite sum that this would create is equal to 1 plus. The 1 was out front. We don't want to even touch that. It's 1 plus the infinite sum of all the decimals that would come together. The way we write this is term 1, which was 0.24, divided by 1 minus the common ratio, which is another way of saying 1 minus 1 over 100. Now, this is going to be equal to 1 plus 0.24 divided by 0. We're going to have 99, because 1 over 100 is 0.01. And then from here, this is going to give us that S infinity is equal to 1 plus. If I do the fraction form of this 0.24 over 99, it's 8 over 33, therefore giving us that, and I'll use an arrow over here, therefore the infinite sum for this one is going to be equal to, if we add 1 and 8 over 33 together, this is 41 over 33. So this would be the value it approaches as we do the infinite sum of the given terms in this series. Awesome. And again, that one's probably the most difficult just because of the way you have to approach it is not very, yes, they're saying use the conceptual approach of geometric series, which you may understand, but the hardest part of the conceptual piece is breaking this decimal apart. Okay, example 7. I really like this one. So this deals with the process of, like, you would see a problem like this in finance, or you would see it in economics a lot, is this idea of maybe not so much a bouncing ball and, decreasing over time and bouncing a ball, but the process in which this is solved is something that is used a lot in financial literacy. So first and foremost, we have some sort of initial value of 3. So you could call this like your initial height in this problem, or in the finance world, an initial investment of this blank value. After each bounce, it rises to 75% of its original value. So this would be essentially saying every time it bounces, or every month maybe that passes, you're losing 25% of the investment on the given original investment. Now, what is the first term in this sequence? It's 3. So we're going to write T1, which is equal to 3.0. And I'm going to write it as 3.0 because they gave it to us as 3.0. The other piece that they said is, what's the common ratio? It's 0.75. They told us that it rises to 75% of its original value. If you wanted to write this as a fraction, we could, because we know that quite well. Now, what is the general term in the sequence? We know this from the previous section. When we talk about a general term in a sequence, they want the Tn. So we're going to look at this and be like, the Tn value is equal to, because we know this is geometric, it must follow from the formula that T1 times Rn minus 1 is the formula we use. And then we're just going to simply plug in the values of Tn is equal to, the first number is 3.0, the common ratio is 0.75, and then the nth value, we don't really know what that is. We're just going to write it as n minus 1 in this situation. But here's the thing we really need to pay attention to, and we're going to resort back to this a couple times here. I really want you to think about what is, when we talk about like this n minus 1, what really is that? Because it's going to help us further down the road in part C and some of the other parts. We want to talk about this as like a certain number of bounces. And here's what I mean by that. If the ball is being dropped from 3, we don't want to consider this a bounce right here. The first bounce occurs right here. And so we're going to say that this is first bounce, this is second bounce, this is third bounce, this is fourth, this is fifth, this is sixth. And there's a reason I'm going to stop at sixth. When we're done with the sixth bounce, we classify this as saying this position right here after the sixth bounce is actually the 7th position here. Or we can say it is the 7th height. And I would highly recommend you write this in here, just indicating for a previous, or for the latter parts to this problem, just indicating what we've just done here, where we're like, okay, we know it starts at 3.0 meters, and then each consecutive bounce that occurs after that, it's actually that after the 6th bounce, that's when we reach that new height, which is going to be called like our 7th height. Now, just trust me on this one. We're kind of putting it all together. So as long as you have that annotation, great. I want you to write the following annotation right next to our n minus 1 here. Underline this, and then we're going to write an arrow to it. And just trust me, because we're going to explain this even further. The n minus 1 is the n number of bounces, or specifically the number of bounces that pass. So if we have 6 bounces, then it's going to put us to a 7th height. If we have 7 bounces, it's going to put us to an 8th height. And here's how that helps us directly in the next part. What height does the ball reach after the 6th bounce? Now, I want you to resort back to the diagram here as we build the formula here. So we're going to say the height at the 6th bounce, which is T6, is equal to, we're going to write this as our, and sorry, I should say that this is going to be our, no, T6 is good. So no, T7, I should have T7 here. So 7th position is equal to, we have 3.0 times 0.75 times 7 minus 1. Now, when we write this as T7 is equal to 3.0 times 0.75 multiplied by 6. Here's why we had to do that in the following way. We know based on the geometric formula here, the geometric formula for any given sequence is written as the following. It's n minus 1, but we wanted it as the sixth bounce. Let's resort back to our diagram. We start up at 3. Here's 1 bounce, here's 2 bounces, here's 3 bounces, here's 4 bounces, here's 5 bounces, here's 6 bounces. What is the height after the sixth bounce? That's the really critical language here. After the sixth bounce. After the sixth bounce, it goes up to that seventh height. And if it's up to that seventh height here, we consider that to be after the sixth bounce, which makes it. So we're actually looking for T7, the seventh position. 1, 2, 3, 4, 5, 6, and 7. That's T7, which occurs after the sixth bounce. And for some of you, you might be like, oh, that's pretty logical, but I just really want to emphasize why I'm writing this as T7 and not as T6, because some of you might just immediately be like, oh, sixth bounce, T6. But you got to think about it as where it's being dropped from. If they said it starts with a bounce and then goes there, that's a different story. But for this situation, we're good with this. Now, you plug this into your calculator. For the seventh position, aka the sixth bounce, we would write this as 0.5339 meters. Perfect. And we can say after the sixth bounce. After the sixth bounce, it's in its seventh position. I know that might seem logical for some of you, but on a first time pass through, it can sometimes be a little difficult. Okay, next piece here. After how many bounces will the ball's height approximately reach 40 centimeters? Now, they're doing something to throw you off here. Here's what they're doing. They write it in centimeters. The whole way we wrote it in meters. So if we want to write this in meters, well, 40 centimeters, there's 100 centimeters in each meter. We're just going to divide that number by 100. When we divide it by 100, this is the value we're looking for. So they're saying, what position is this where it reaches this height of 40 centimeters, which in our situation is 40 meters? We're going to write out our formula, Tn, which is equal to, we're going to write 0.40, the height that we're looking for, which is equal to the T1, which is 3.0, times the common ratio of 75% of its original height, or of that previous bounce, times the n minus 1. We don't know what the n is, so we got to write that there. What we're going to do is divide both sides by 3.0 because we want to get rid of the coefficient. When we take 0.40 and divide it by 3, we get 0.13 repeated. I'm going to hold on to all that. And more importantly, 1 with the 3 repeated. I don't want to clump those two together, which is equal to 0.75 times n minus 1. Hey, look at this. We're going to do our log routine again. We know that we've done this before where we want to solve for the n from the exponent. We take the log of both sides. So I'm going to write this as log of 0.13 repeated is equal to the log of 0.75 all raised to the power of n minus 1. The beauty of this log format is that we can write the following. This is going to be log of 0.13 repeated is equal to the n minus 1 can now be transitioned to the front of the logarithm, and we write log of the 0.75. We're going to divide both sides by the log 0.75 as such. And whoops, it would help if I actually wrote the log in there. So I'm going to make sure I write log of 0.75. And then in our calculators, if we actually calculate this value, log 0.13 repeated divided by 0.75 log is equal to 7, which is equal to n minus 1. Now, some of you would be very quick to jump on this and be like, oh, we plus 1 to the other side and n equals 8, and yay, we got our answer. But remember what we said, and we defined this as originally. The n minus 1 is the number of bounces. And so they're saying, after how many bounces will it reach that height? The n minus 1 is the number of bounces. I highly recommend you annotate that here. This is the number of bounces. And if this is the number of bounces, then therefore the n minus 1 is the solution, and we can say that there are 7 bounces to get to a height of 0.40 meters. And I apologize for going over the next problem there. That might be a little bit distracting to some of you. Hopefully that's okay there. So again, we just want to make sure that we don't jump the gun and we add one there. We got to be very careful. Again, we could even just do this right here if we wanted to go back up to our diagram very quickly and just kind of talk about this for a second, because this may actually help us on our next one. We can look at this and say, well, if we know that they're decreasing and decreasing in terms of their 75% of the previous height that they were at, then if I take 3.0 and I multiply it by 0.75, I'm going to get 2.25 meters. And then I could continue this pattern and go below and be like, well, to get to the next ball bounce, I would go 2.25, 2.25, and multiply it by 0.75. And that would give me 1.6875. And then you could just continue that pattern over and over and over. And they're apparently saying that after the seventh bounce, which occurs down here, I'm going to write it in the orange. This is our seventh bounce. That means that the height of the ball at this position, which is actually the eighth height, at the eighth height, this is going to be the 0.40 meters. That's where they're referring to the ball being at that height. Awesome. Okay. Now, and again, that would be the eighth term or the eighth height if we're thinking about it in that given way. All right. Now, determine the total vertical height of the ball as it's traveled and then when it comes to rest. Here's how we got to think about this. This is another quite complicated one. However, you can break it apart in a very logical way. So we know that if we calculate using this notation of an infinite geometric sequence, we can take that original height and divide it by 1 minus the common ratio, which is 0.75. And apparently this would give us the overall heights in terms of the ball bouncing. But we want to break this apart and say, this is actually the infinite geometric series for when it's falling out of the air, because the original start position was 3. So this would be for all the parts that it's falling and all the pieces, and which we can go back up to our diagram here. When we talk about it as 3 divided by 1 minus 0.75, we're talking about we add this part, this part, this part, this part, this part, and this part. That's all the parts we're adding when we talk about that 3 divided by 1 minus 0.75, which means if we want to get the total height of all the segments, we actually have to then add all of these pieces, the left piece, the left piece, the left piece, and the left piece. To do that, we're going to take the return height, because if it drops by 3 and then we start the geometric sequence of the falling position after 3, we're going to start the rising part after it reaches 2.25. So all of my rising pieces start at 2.25 and then decrease from there. So let's add that into our formula here. It's going to be a 2-part geometric where we have the first part, which is the falling, and then we have our 2.25 divided by the 1 minus 0.75, which represents all of the rising parts. Awesome. Now, in your calculator, you could plug these in and say, well, therefore, the S infinity, or the total heights calculated, would be the first part where it's falling adds up to 12 meters. The part where it's rising is all of the 9 meters, I should say. And when we put those things together, 9 plus 12 gives us 21 meters total height. And you could just write total, or you could write total height. I like the idea of writing total height just to be very specific. And then that's our answer there, saying that this is the approached value of the total of all of the heights as it rises and falls and rises and falls all the way to its resting position. All right, here's where you're going to want to get some practice with the assignment. At this point, I would definitely recommend do as many of the assignment problems as you can. Ask questions to your neighbors, to me, whatever will help you. See me in tutorials. And then at this point, you're going to want to move on to the review. There's lots of questions here. There's the answers on the next page. Make sure you're taking advantage of this as you prep for your unit test. All right, good luck with your practice.